Right now, as you watch this, an immense force is moving toward us from the depths of space, not a rogue planet or a wandering black hole, but something far more subtle and yet equally powerful. A vast interstellar cloud, made up of gas and dust thinner than the finest silk, is drifting closer to our solar system. You can't see it with your eyes, and it won't light up the sky like a comet, but its arrival could change the very fabric of our cosmic neighborhood. This isn't a distant possibility or a theoretical scenario, it's happening, and the effects could ripple across centuries, reshaping the protective bubble that shields Earth from the harshness of interstellar space. Think of the heliosphere as our solar system's invisible shield, a giant bubble created by the sun's outward flow of charged particles. It's what keeps dangerous cosmic rays at bay, safeguarding not just our technology and satellites, but life itself. Now, imagine that shield bending, warping, or even shrinking under the pressure of this approaching cloud. What happens then? Could Earth suddenly find itself exposed to higher levels of radiation? Could our climate or even the stability of our atmosphere be affected? These aren't just questions for scientists, they're questions for all of us, because this cosmic event doesn't just belong to astronomers. It's a story about our home, our future, and how fragile our place in the universe truly is. But here's what's truly astonishing. This cloud isn't some random accident of space. It's a remnant of ancient stellar explosions, a whisper from stars that died long before our sun even ignited. And as it nears, it offers us a front-row seat to one of the rarest and most profound interactions in the cosmos. Over the next few minutes, we'll unravel the science behind this celestial encounter, how it was discovered, what it means for the heliosphere, and whether humanity should be concerned. Along the way, we'll explore how something so diffuse, so seemingly insignificant, could hold the power to alter the boundaries of our solar system. So settle in, because this isn't just a story about space. It's a story about us and how we're all connected to the grand, ever-changing tapestry of the universe. Picture the sun not just as a ball of light in our sky, but as an engine constantly blasting out a stream of charged particles, a solar wind racing outward at nearly 1,000,000 miles per hour. This wind doesn't just vanish into the void. Instead, it carves out a vast, invisible cocoon around our entire solar system, pushing against the thin gas and dust floating between the stars. That's the heliosphere, a protective bubble so large it extends more than twice the distance to Pluto. Its boundary isn't solid like a wall, but more like a turbulent shoreline where the sun's influence finally gives way to the interstellar medium. What makes this cosmic shield so crucial? Beyond blocking up to 70% of harmful galactic cosmic rays, it also filters out interstellar dust that could otherwise bombard our planets. Without it, Earth's atmosphere might have eroded over billions of years, and life might never have gained a foothold. But here's the twist: the heliosphere isn't static. Like a balloon caught in shifting winds, its shape changes constantly. When solar activity is high, it swells outward. During quieter periods, it contracts. And when something massive, like an interstellar cloud, collides with it, the entire structure can warp, ripple, or even shrink dramatically. Scientists discovered the heliosphere's dynamic nature only in recent decades, thanks to spacecraft like Voyager 1 and 2, which crossed its outer edge and tasted true interstellar space. Those missions revealed something startling. The boundary isn't smooth or symmetrical. Instead, it's riddled with magnetic bubbles and turbulent currents, a chaotic frontier where the sun's domain meets the galaxy. Now, with this interstellar cloud approaching, We're about to witness a rare cosmic experiment, one where an external force could compress or distort our protective shield in ways we've never seen before. The real mystery lies in how the heliosphere responds to pressure. Some models suggest it could recoil like a spring, bouncing back after the cloud passes. Others warn of longer-lasting effects, like a permanent dent or a weakened barrier letting in more radiation. Either way, this isn't just about physics, it's about the delicate balance that keeps our planet safe. If the heliosphere falters, even temporarily, the consequences could ripple through everything from satellite communications to Earth's climate. And that's why understanding this shield isn't just academic. It's a matter of cosmic survival. The first hints of this interstellar visitor came not from a dramatic flash in the night sky, but from subtle distortions in the light of distant stars. In the 1970s, astronomers noticed peculiar absorption lines in stellar spectra, tiny gaps where specific wavelengths of starlight were being absorbed by something invisible between us and those faraway suns. At first, these readings seemed like minor anomalies, just another quirk in the vast cosmic dataset. But over decades, as observations accumulated, a pattern emerged. Whatever was causing these distortions wasn't stationary, it was moving, and moving toward us. The breakthrough came when space telescopes like Hubble and later missions equipped with ultraviolet and X-ray detectors began mapping the interstellar medium in unprecedented detail. They revealed a vast, diffuse structure now known as the local interstellar cloud, a wispy filament of ionized hydrogen and helium, peppered with microscopic dust grains stretching across dozens of light years. What makes this cloud so fascinating isn't just its size or composition, but its history. Traces of heavier elements like iron and silicon mixed into its gases tell a story of ancient supernova, suggesting this cloud is the debris from stellar explosions that occurred millions of years ago. But how do you track something so tenuous? Unlike a comet or asteroid, this cloud doesn't reflect sunlight or emit visible radiation. Instead, scientists rely on two key signatures: the way it scatters extreme ultraviolet light from nearby stars and the faint pressure it exerts on the heliosphere's outer layers. Spacecraft like NASA Interstellar Boundary Explorer, or IBEX, have spent years mapping these invisible interactions, detecting energetic neutral atoms that form when solar wind particles collide with the cloud's material. These collisions create a sort of cosmic echo, allowing researchers to trace the cloud's contours as clearly as if they were seeing it with their eyes. What's truly remarkable is how recent technology has transformed our understanding. Just 20 years ago, many astronomers assumed the space between stars was relatively uniform and unchanging. Now we know it's a dynamic, ever-shifting sea of clouds and bubbles, each with its own density, temperature, and velocity. The cloud approaching us isn't some solitary wanderer. It's part of a complex ecosystem shaped by stellar winds, supernova remnants, and the Milky Way's own magnetic fields. And as it nears, it's offering us something rare, a chance to study an interstellar environment up close without ever leaving our solar system. The urgency behind this research isn't just academic. By analyzing the cloud's composition and trajectory, scientists can predict how it might compress or distort the heliosphere. Some theories suggest its magnetic fields could reconfigure the solar wind's flow, potentially funneling more cosmic rays toward the inner solar system. Others point to the dust grains within the cloud particles, so fine they're barely visible, yet numerous enough to subtly alter the chemistry of interplanetary space. These aren't abstract concerns. Even minor changes to the heliosphere could impact satellite operations, astronaut safety, and Earth's exposure to high-energy radiation. Perhaps the most surprising revelation is how much we still don't know. For all our advancements, the local interstellar cloud remains full of mysteries. Why does it move at the speed it does? What exact mix of elements does it contain? And most crucially, how will it behave when it fully encounters the heliosphere's boundary? Every new observation peels back another layer, revealing a story written not in rock or ice, but in the faintest whispers of ionized gas, a story that's been unfolding for millions of years, and one that's now reaching its next chapter right here in our cosmic backyard. What makes this interstellar cloud so different from the empty void we often picture between the stars? It's not just a wispy haze, it's a dynamic, chaotic structure, more like a stormy ocean than a calm lake. At its core, hydrogen and helium dominate, but scattered among them are trace elements like iron, silicon, and even carbon, atoms forged in the hearts of ancient stars and scattered across space by violent supernova. These heavier elements act like cosmic fingerprints, revealing the cloud's explosive origins. Scientists believe this material might have been ejected from a dying star millions of years ago, a stellar farewell that's now drifting toward us with consequences we're only beginning to understand. The cloud's density is another key factor. While the average interstellar medium is so thin that a single grain of dust might span miles, this cloud is packed tightly enough to exert real pressure on the heliosphere. Imagine the difference between walking through open air and wading through waist-deep water. That's the kind of resistance our solar system's boundary could soon face. But it's not just the sheer amount of material that matters. The cloud's internal structure is laced with magnetic fields, twisted into knots and loops by ancient shock waves. These magnetic tangles could act like cosmic battering rams, amplifying the cloud's impact as it presses against the heliosphere's outer layers. Then there's the turbulence. Unlike the smooth, steady flow of the solar wind, this cloud is a churning mess of currents and eddies, with pockets of gas moving at different speeds and directions. Some regions might slip past the heliosphere with little effect, while others could deliver concentrated blows, denting our protective bubble unevenly. It's this unpredictability that makes the cloud so fascinating and so challenging to model. Supercomputers running simulations struggle to capture every ripple and twist, leaving scientists to wonder, will the heliosphere bend uniformly, or will it crumple in some areas while holding firm in others? The answer could lie in the cloud's chemistry. Those trace elements we mentioned earlier don't just tell us where the cloud came from, they also change how it behaves. Iron and silicon atoms, for example, can absorb and re-emit radiation, subtly heating the cloud's gases and altering their movement. Even the dust grains, tiny as they are, play a role. When solar wind particles slam into them, they can scatter or absorb energy, creating shock fronts that ripple through the cloud like sonic booms. These microscopic interactions add up, potentially turning the entire cloud into a more formidable force than its size alone would suggest. One of the most startling discoveries came from spacecraft data showing how the cloud's magnetic fields align. Instead of pointing in random directions, many of them seem to follow a loose pattern, as if the cloud retains some memory of the stellar explosion that birthed it. This alignment could be crucial when the cloud meets the heliosphere's own magnetic fields. If they clash head-on, the resulting turbulence might send unpredictable waves rippling back toward the inner solar system. But if they slip past each other like two combs intertwining, the effect could be far gentler. Right now, no one knows for sure, which is why astronomers are racing to map every detail before the encounter intensifies. What's clear is that this isn't just a passive cloud drifting through space. It's an active, evolving structure carrying the echoes of long-dead stars and the potential to reshape our solar system's defenses. As it nears, it challenges everything we thought we knew about the space between stars and reminds us that even the faintest cosmic whispers can have thunderous consequences. This interstellar cloud didn't begin its journey toward us yesterday or even in humanity's lifetime. It's been carving its path through the galaxy for millions of years, buffeted by forces we're only beginning to comprehend. Picture it like a cosmic leaf caught in the Milky Way's winds, shaped by gravitational tides from passing stars and the subtle push of supernova shockwaves. Along the way, it's collided with other interstellar structures, each encounter leaving an imprint in its chemistry and momentum. Some of these collisions may have stripped material away, while others deposited new elements, turning the cloud into a layered record of galactic history. What's truly remarkable is how predictable its motion appears when viewed on cosmic timescales. By analyzing its current speed and trajectory, astronomers have traced its path backward through time, revealing origins that predate human civilization by epochs. The cloud likely formed in the turbulent aftermath of a stellar explosion, where intense radiation and shockwaves compressed nearby gas into dense knots. Over millennia, the Milky Way's rotation carried it through different galactic environments, some sparse and quiet, others dense with stellar activity. Each region left its mark, whether through ultraviolet radiation altering the cloud's chemistry or magnetic fields sculpting its shape. Now, as it nears our solar system, the cloud's journey enters a critical phase. Current estimates suggest it's moving at roughly 15 to 20 kilometers per second relative to the Sun, a pace that might seem sluggish until you consider the sheer scale of space. At that speed, it could take centuries or even millennia for the cloud to fully envelop the heliosphere, meaning this won't be a fleeting event but a gradual, persistent pressure on our cosmic shield. The duration of its influence depends on its size, something astronomers are still refining. If the cloud is denser than expected, its effects could linger longer, potentially altering the heliosphere's shape for generations. But here's where the story gets even more intriguing. This isn't the first time our solar system has encountered such a structure. Geological and isotopic evidence suggests Earth may have passed through similar interstellar clouds in the distant past, leaving subtle traces in ancient ice cores and sediment layers. Some researchers speculate these past encounters could explain certain climate shifts or spikes in radiation levels recorded in Earth's geological record. Now, for the first time in human history, we have the technology to watch this process unfold in real time, not just as passive observers, but as active documentarians of a cosmic event that could redefine our understanding of the solar system's place in the galaxy. The cloud's long journey also raises a profound question. How many other interstellar structures are drifting toward us unseen? Our galaxy is filled with similar clouds, some larger, some more dense, all moving along their own ancient paths. Mapping their trajectories could give us a kind of cosmic weather forecast, predicting when the next major interaction might occur. For now, this particular cloud serves as both a scientific opportunity and a gentle reminder. The space between stars isn't empty. It's alive with movement, history, and forces that, given enough time, will always find their way to our doorstep. Right now, we're living in the calm before a cosmic storm, one that won't arrive in our lifetimes or even in the next 100 generations, but is already set in motion. The interstellar cloud's approach isn't a sudden event. It's a slow-motion collision, a dance of gravity and momentum that's been unfolding for millennia. Current models place the first tangible effects on our heliosphere within the next 2,000 to 3,000 years. That might sound like an eternity, but in the life of a solar system, it's barely a heartbeat. The first signs won't be dramatic. There won't be a visible rift in the sky or a sudden surge in radiation. Instead, the changes will be subtle shifts in the solar wind's behavior, faint distortions in the magnetic fields at the edge of our solar system. Spacecraft like Voyager and Ibex, or their future successors, might detect ripples in the heliosphere's boundary long before Earth feels any consequences. These early warnings could come as tiny fluctuations in the flow of energetic neutral atoms, or as unexpected twists in the magnetic field lines that usually shield us. As the cloud's influence grows, its effects will cascade over centuries. The heliosphere, now shaped like a windsock billowing in the solar wind, could begin to compress on one side, its boundary pushed inward by the cloud's pressure. Some simulations suggest it might flatten, like a rubber ball squeezed between two hands. Others predict a more asymmetrical collapse, with one hemisphere of the solar system bearing the brunt of the interaction. The exact outcome depends on variables we're still mapping: the cloud's density, its magnetic field orientation, even the sun's own activity during the encounter. What's fascinating is how long the process could last. Unlike a comet's flyby or a meteor impact, this won't be over in days or years. The cloud's passage might span tens of thousands of years, with its peak influence lasting centuries. That means generations of astronomers will have front-row seats to a celestial transformation, watching as the heliosphere bends, adjusts, and eventually, hopefully, rebounds. The real question isn't just when the cloud arrives, but how its effects will ripple inward. Cosmic rays, usually filtered by the heliosphere, could gradually increase near Earth, potentially affecting satellite electronics or even atmospheric chemistry. The solar wind, no longer flowing unimpeded, might develop turbulent eddies, altering the trajectories of interplanetary dust or comets in the outer solar system. And if the heliosphere contracts enough, the very definition of interstellar space could shift closer to home, with Pluto's orbit someday lying near its frayed edge. This timeline isn't just a scientific curiosity, it's a reminder of how dynamic our cosmic neighborhood truly is. The same forces that shaped Earth's climate over millennia, the same slow cosmic rhythms that guided the evolution of life, are still at work. And while the cloud's full impact lies far in the future, its approach is a humbling lesson. The universe doesn't operate on human schedules. It moves at its own pace, and we're just beginning to learn how to read its clock. The heliosphere doesn't just exist, it reacts, like a living membrane responding to the slightest touch. Picture it as a vast, invisible force field, constantly adjusting to the push and pull of the cosmos. When the interstellar cloud finally makes contact, its gentle but relentless pressure will begin reshaping this boundary, squeezing it inward like a balloon pressed between two hands. But this isn't a simple, uniform collapse. The heliosphere's response will be chaotic, dynamic, and full of surprises, revealing just how complex our solar system's shield truly is. At the heart of this transformation is a clash of titanic forces. On one side, the solar wind, a ceaseless stream of charged particles racing outward from the sun at hundreds of kilometers per second. On the other, the interstellar cloud's own mix of gas, dust, and magnetic fields, drifting toward us with the quiet inevitability of a tide. Where these two meet, the collision won't be a clean break but a turbulent mixing zone, a cosmic frontier where particles ricochet, merge, and accelerate to energies we rarely see inside the solar system. This region, known as the heliopause, could become a hotspot for particle acceleration, generating radiation that might ripple inward over time. What's fascinating is how uneven this compression could be. The heliosphere isn't a perfect sphere. It's already dented and distorted by the galaxy's magnetic fields and the solar system's motion through space. As the cloud presses closer, some areas might crumple faster than others, creating asymmetrical bulges or folds in our protective bubble. Imagine pressing your palm into a water balloon. The side under your hand flattens while the opposite side stretches thin. That's the kind of distortion scientists expect, with one hemisphere of the heliosphere potentially bearing the brunt of the cloud's impact while the other remains relatively untouched. The real wild card lies in the magnetic fields. Both the solar wind and the interstellar cloud carry their own invisible lines of force, and when they tangle, the results could be dramatic. If the cloud's fields align in opposition to the sun's, they might create magnetic reconnection events, sudden bursts of energy that fling particles outward like cosmic slingshots. These outbursts could punch temporary holes in the heliosphere's defenses, allowing more interstellar material to seep through. Alternatively, if the fields merge smoothly, the compression might be gentler, like a hand guiding the heliosphere into a new shape rather than crushing it outright. One of the most striking consequences could be the birth of new structures at the edge of our solar system. Just as wind sculpts sand dunes, the interstellar cloud's pressure might carve ripples or shock waves into the heliopause. These features wouldn't just be curiosities, they could act as cosmic mirrors, reflecting solar wind particles back toward the inner solar system or funneling interstellar dust into previously shielded regions. Over centuries, this could subtly alter the chemistry of interplanetary space, with implications for everything from comet orbits to the behavior of distant spacecraft. But here's the twist: the heliosphere isn't helpless. It's resilient, capable of fighting back against external pressure. When compressed, the solar wind might intensify, like a gust of air squeezed from a balloon's neck. This surge could temporarily stabilize the boundary, buying time for the heliosphere to adapt. Some models even suggest the sun itself might respond, with increased magnetic activity or shifts in solar wind output as the star senses the growing pressure at its domain's edge. It's a cosmic feedback loop, where the sun and its surroundings constantly adjust to one another in a dance older than humanity itself. What makes this moment so extraordinary is the chance to witness a fundamental cosmic process in action. The heliosphere has faced interstellar clouds before geological records hint at past encounters, but never while we've had the tools to study it. Every ripple, every particle surge, every magnetic tremor will be a clue, helping us decode the hidden language of the interstellar medium. And as the cloud's influence grows, it won't just reshape the heliosphere, it'll reshape our understanding of where the solar system ends and the galaxy begins. One of the most immediate consequences of a compressed heliosphere would be the floodgate effect, a potential surge in cosmic rays reaching inner solar system. These aren't just random particles, they're atomic bullets traveling near light speed, remnants of supernova and other violent cosmic events. Normally, the heliosphere deflects about 70% of them, but if its boundary crumples under the interstellar cloud's pressure, that filtration system could fail. The first signs might appear in satellite data: increased glitches in onboard electronics or solar panels degrading faster than expected. Over time, even Earth's surface could register higher radiation levels, particularly at high altitudes where the atmosphere's shielding is thinnest. For astronauts, the risks are stark. A mission to Mars during peak compression could expose crews to radiation doses equivalent to decades of natural background exposure on Earth. Current spacecraft shielding designed for the heliosphere's protection might suddenly prove inadequate, forcing redesigns with thicker hulls or innovative magnetic deflectors. But the challenge extends beyond human exploration. Cosmic rays can ionize Earth's upper atmosphere, altering cloud formation patterns and potentially influencing weather systems. Historical ice core studies reveal periods of heightened cosmic ray activity coinciding with climate shifts, suggesting this interstellar encounter could leave subtle fingerprints in our planet's meteorological records. The technological fallout could be equally profound. Increased particle bombardment might degrade satellite components faster, shortening lifespans for GPS networks, communication satellites, and Earth-observing systems. High-energy particles striking computer chips can cause bit flips, random errors where zeros become ones or vice versa, potentially scrambling critical data. In extreme scenarios, cascading failures could disrupt global navigation or financial systems reliant on precise timing signals from space. Engineers are already studying solutions, from radiation-hardened electronics to AI systems that can detect and correct cosmic ray-induced errors in real time. Yet the most intriguing possibility lies in the biological realm. While Earth's atmosphere and magnetic field provide robust protection, some studies suggest prolonged increases in cosmic radiation might subtly alter mutation rates in living organisms. This wouldn't be an apocalyptic scenario. Life has endured far worse over geological time, but it could accelerate evolutionary pressures in sensitive ecosystems. Meanwhile, at the molecular level, cosmic rays can break chemical bonds in our atmosphere, potentially affecting ozone chemistry or even creating rare isotopes that weren't present before the cloud's arrival. What makes this situation unique is its timescale. Unlike solar storms that come and go in hours, the cloud's influence could persist for centuries, creating a sustained radiation environment unlike anything in recorded history. Space agencies might need to develop early warning systems tracking heliosphere deformation, giving civilizations decades to adapt. The irony is profound. A seemingly empty cloud, thinner than any laboratory vacuum, might ultimately force us to rethink how we design technology, explore space, and even understand our place in this evolving cosmic ecosystem. The journey beyond our solar system was never going to be easy, but the approaching interstellar cloud adds a new layer of complexity to humanity's interstellar ambitions. Picture a future probe like NASA's proposed Interstellar Probe mission, designed to venture past the heliosphere's edge. Except now, its path would cut through a turbulent frontier reshaped by external forces. Instead of sailing through the relatively calm waters of our sun's influence, it might encounter swirling magnetic eddies and pockets of denser interstellar material, turning a straight shot into an obstacle course. Even minor deviations could compound over light years, potentially throwing a spacecraft off course by the time it reaches another star. Communication with these distant explorers could become another critical challenge. The cloud's ionized gases might scatter or absorb radio signals, creating static in transmissions that already take years to reach Earth. Imagine sending corrective commands to a probe halfway to Alpha Centauri, only for the message to arrive garbled or weakened by interstellar interference. Space agencies may need to develop entirely new protocols, perhaps laser-based systems or relay networks, to maintain contact across this distorted boundary. For astronauts, the risks are even more immediate. Cosmic radiation, already a formidable hurdle for Mars missions, could intensify as the heliosphere's defenses waver. A ship bound for the outer planets might suddenly require shielding twice as thick, or need to reroute entirely to avoid regions where the cloud's pressure has funneled dangerous particles inward. Some theorists suggest future crews could use the cloud's own magnetic fields as a makeshift shield, navigating their vessels along these invisible contours like sailors riding ocean currents. The irony is striking. The same interstellar medium that inspires dreams of exploration also complicates it. Technologies we take for granted today, solar power, magnetic shielding, even basic trajectory calculations, might need reinvention to account for this evolving environment. Engineers are already brainstorming solutions, from adaptive plasma shields that respond to fluctuating radiation levels to AI pilots capable of rerouting missions in real time based on heliosphere telemetry. Yet amid these challenges lies an unprecedented opportunity. Every probe sent into this altered frontier will return data we've never had before, a chance to study how spacecraft interact with undisturbed interstellar material. What we learn could unlock faster propulsion methods, better shielding, or even new ways to harness cosmic forces. The cloud doesn't just raise obstacles, it offers a live testing ground for technologies that might one day carry humans to the stars. The real question isn't whether we'll adapt, but how creatively. History shows that each new barrier in space exploration has sparked innovation, from the heat shields of the Apollo era to the radiation-hardened electronics of modern satellites. This interstellar encounter could be the catalyst for the next great leap, pushing us to design missions as dynamic and resilient as the cosmos itself. The cloud may reshape our heliosphere, but it won't stop humanity's reach. It'll simply redefine how far we're willing to go. Earth's geological archives hold cryptic evidence of past encounters with interstellar clouds, layers of ice, stone, and sediment that serve as a cosmic diary written over eons. In Antarctica and Greenland, ice cores drilled from ancient glaciers reveal sudden spikes in rare isotopes like iron-60, a radioactive form of iron that forms only in supernova. These telltale atoms, preserved like interstellar dust trapped in amber, suggest our planet was showered with stellar debris around 2.5 million years ago, likely from a nearby exploding star. But there's more to the story. Mixed with these isotopes are traces of beryllium-10, another cosmic marker produced when heightened galactic cosmic rays strike Earth's atmosphere. Together, they paint a picture of a time when our solar system's protective shield may have weakened, allowing more interstellar material and radiation to reach us. The timing of these events aligns eerily with pivotal moments in Earth's climate history. Sediment records from the same period show global cooling trends, with some regions experiencing abrupt shifts in rainfall patterns. While no single interstellar encounter can explain all of Earth's climatic changes, the correlation raises provocative questions. Could a compressed heliosphere have altered the flow of cosmic rays enough to affect cloud formation? Some researchers point to the Svensmark hypothesis, which suggests cosmic rays seed low-level clouds by ionizing atmospheric particles. More clouds mean more sunlight reflected back into space, potentially cooling the planet. It's a controversial idea, but if even partially true, past interstellar clouds might have left their fingerprints on Earth's thermostat. Beyond ice cores, the fossil record offers tantalizing clues. The late Pliocene epoch, when these isotope spikes occurred, saw significant marine extinctions, particularly among deep-sea species sensitive to environmental changes. Meanwhile, land animals faced prolonged droughts that reshaped ecosystems. While terrestrial extinctions were less dramatic, the timing suggests a planet under stress, not from a single catastrophic event, but from sustained cosmic pressure. Of course, Earth's climate is a complex system influenced by countless factors, from volcanic activity to ocean currents. Isolating the role of interstellar clouds requires meticulous detective work, comparing isotope layers with fossil pollen, tree rings, and seafloor sediments to reconstruct a coherent timeline. Meteorites provide another piece of the puzzle. Certain space rocks contain unusual concentrations of noble gases like neon and xenon, with isotopic ratios that don't match the solar system's average. These anomalies, trapped for billions of years, resemble the chemical signatures of modern interstellar clouds. The implication is startling. Some meteorites might be time capsules preserving material from ancient encounters, physical proof that our solar system has weathered similar events before. Perhaps the most revealing case comes from the Jurassic period. Around 150 million years ago, Earth experienced a prolonged drop in sea levels, and a spike in carbon-13 isotopes, both potential signs of cooler global temperatures. Around the same time, the solar system was likely passing through the Orion Spur, a dense filament of the Milky Way's spiral arm packed with interstellar material. While correlation isn't causation, the parallel is striking. If the heliosphere contracted then, as it might again, the resulting cosmic ray flux could have influenced everything from mutation rates in early mammals to the chemistry of shallow seas where ammonites thrive. What makes these historical echoes so valuable isn't just their warning, it's their reassurance. Life persisted through every past encounter, adapting to the subtle cosmic rhythms. The current cloud's approach isn't an existential threat, but a natural phase in our solar system's journey through the galaxy. By studying these ancient traces, scientists aren't just preparing for the future, they're decoding a message written in stardust, one that reminds us how deeply Earth's story is woven into the fabric of the cosmos. The sun isn't just a glowing orb in the sky, it's a churning powerhouse of magnetic energy, and its temperament holds the key to our solar system's defense. Every 11 years or so, the sun cycles between periods of intense activity and relative calm, like a cosmic heartbeat. During its most active phases, solar flares and coronal mass ejections blast vast amounts of charged particles into space, supercharging the solar wind and inflating the heliosphere like a balloon. This expansion could be our first line of defense against the interstellar cloud's approach, pushing the boundary outward and buying Earth extra shielding. But when the sun quiets down, that protective bubble contracts, leaving the heliosphere more susceptible to external pressures. What's fascinating is how unpredictable these cycles can be. Historical records show periods where the sun remained eerily silent for decades, like the Maunder minimum in the 17th century, when sunspots nearly vanished and Europe plunged into a little ice age. If such a solar lull coincides with the cloud's peak pressure, the heliosphere could shrink dramatically, compressing our cosmic shield to its thinnest in millennia. Conversely, an unusually active sun might counteract the cloud's influence entirely, its furious outbursts acting like a buffer against the interstellar tide. The delicate balance between these two forces, the sun's internal dynamo and the cloud's external push, will determine how much of the universe's harshness reaches our doorstep. Scientists track these solar moods using spacecraft like NASA's Solar Dynamics Observatory, which captures the sun's magnetic field in mesmerizing detail. Twisted loops of plasma, larger than Earth, arc across its surface, while sunspots reveal where magnetic energy knots and erupts. These features aren't just beautiful, they're clues to the sun's coming behavior. By mapping magnetic field strength and complexity, researchers can predict whether the next solar cycle will roar or whisper. Right now, we're entering a period of heightened activity, with some models suggesting the approaching peak could be among the strongest in recorded history. That's good news for the heliosphere, but it's only a temporary reprieve. The real challenge lies in the long game. Even if the sun's current vigor softens the cloud's initial impact, solar cycles are fleeting. The interstellar cloud's passage, on the other hand, will span thousands of years, far longer than any single period of high or low solar activity. That means the heliosphere's resilience will ultimately depend on averages, not just the sun's momentary outbursts, but its overall behavior across centuries. If future cycles trend weaker, the cloud's pressure could slowly erode our defenses. If they trend stronger, the heliosphere might hold firm. One of the most intriguing possibilities is feedback, the idea that the sun could sense and respond to the cloud's encroachment. Some theories suggest that increased pressure at the heliosphere's edge might trigger adjustments in the solar wind, as if the sun itself is fighting to maintain equilibrium. It's a cosmic tug-of-war, with the sun's magnetic field acting as both shield and sword. And while we can't control these vast forces, understanding them gives us something equally valuable: the power to anticipate, adapt, and marvel at the intricate dance between our star and the galaxy beyond. To understand what might happen when this interstellar cloud reaches us, scientists aren't just guessing, they're building cosmic laboratories inside supercomputers. These aren't ordinary simulations, they're digital recreations of our entire heliosphere, down to the intricate interplay of magnetic fields and charged particles, all designed to test how this invisible shield might bend or buckle under pressure. One such model, run at NASA Ames Research Center, treats the solar wind like a river flowing through space, while the interstellar cloud acts as an incoming tide, slow, relentless, and capable of reshaping everything in its path. The results are mesmerizing. Some iterations show the heliosphere compressing smoothly, like a balloon gently squeezed. Others reveal chaotic turbulence, with magnetic field lines snapping and reconnecting in bursts of energy that send shockwaves rippling inward. The most surprising simulations suggest the heliosphere might not just shrink, it could temporarily split. In these scenarios, the cloud's magnetic fields create fissures in our protective bubble, like cracks in a windshield under pressure. These gaps wouldn't last forever. The sun's constant outflow of particles would eventually patch them, but during that window, cosmic rays could flood into the inner solar system at levels not seen in millennia. What's fascinating is how localized these effects might be. One simulation shows Earth's orbit remaining relatively shielded while Mars bears the brunt of increased radiation, a potential headache for future colonists. Another predicts the opposite, with Jupiter's massive magnetic field funneling particles away from the outer planets and toward us. These models aren't just academic exercises. They're helping scientists identify early warning signs, subtle changes in the solar wind, or shifts in the heliopose's shape that could signal the cloud's influence is ramping up. Some teams are even training machine learning algorithms to spot these patterns in real-time data from spacecraft like IBEX and Voyager, turning these far-flung probes into cosmic canaries in a coal mine. But the simulations also reveal something deeper. The heliosphere isn't just a passive barrier. It's an active participant in this dance, constantly adjusting its shape and strength in response to the interstellar environment. When compressed, some models show it rebounding like a spring, while others suggest it might settle into a permanently altered configuration, a new normal for our solar system's defenses. Yet for all their complexity, these digital experiments come with caveats. The interstellar cloud's exact density, magnetic field orientation, and internal turbulence remain educated guesses, meaning every simulation is only as good as the assumptions fed into it. That's where observations from upcoming missions like the Interstellar Mapping and Acceleration Probe, or EMAP, will prove invaluable. Scheduled to launch later this decade, EMAP will map the heliosphere's boundary in unprecedented detail, offering real-world data to refine these virtual experiments. Until then, each supercomputer run is a glimpse into a possible future, one where humanity might need to adapt to a solar system that no longer plays by the old rules. What's striking is how much these models have evolved in just a few years. Early attempts treated the heliosphere as a simple, symmetrical bubble. Today's simulations capture its true complexity, the asymmetries caused by the solar system's motion through the galaxy, the chaotic magnetic froth at the boundary, even the way passing stars might have tugged on it over millennia. It's a reminder that we're not just observers of this cosmic drama. We're participants, using every tool at our disposal to read the universe's next move before it happens. And as the cloud draws nearer, these digital crystal balls will only grow sharper, helping us prepare for a future written not in stone, but in stardust and solar wind. Our solar system's approaching interstellar cloud might seem like a solitary wanderer, but it's far from alone in the galaxy. Astronomers have turned their telescopes toward the Milky Way's shimmering expanse, hunting for similar structures drifting between the stars. What they've found rewrites our understanding of the cosmos. Instead of empty voids, interstellar space teems with these ghostly clouds, each with its own density, chemistry, and potential to reshape planetary systems. The European Space Agency's Gaia mission has mapped over a dozen major clouds within just a few thousand light-years of Earth, some dwarfing our local interstellar cloud by a factor of 100. Take the G cloud, for instance, a sprawling structure near the star Alpha Centauri that shares eerie similarities with our approaching visitor. Both contain traces of iron and silicon from ancient supernova, and both move at comparable speeds through the galaxy. But crucial differences emerge upon closer inspection. The G cloud's magnetic fields align more chaotically, suggesting a more violent origin story, while its dust grains show unusual spikes in carbon content. These variations matter because they hint at how differently such clouds might interact with planetary systems. A cloud rich in carbon dust, for example, could seed organic molecules across a star system, or clog sensitive spacecraft instruments with microscopic debris. Then there's the terrifying case of the Smith Cloud, a hydrogen behemoth larger than 30 million suns barreling toward the Milky Way's disk at nearly 200 kilometers per second. Unlike our relatively gentle interstellar visitor, this cloud's sheer momentum could trigger shockwaves capable of compressing entire star-forming regions. While it won't reach our neighborhood for millions of years, its existence proves some interstellar clouds carry enough kinetic energy to reshape galaxies. By comparison, our local interstellar cloud is a whisper, but that doesn't mean all whispers are harmless. Cataloging these cosmic nomads reveals an unexpected pattern. Many appear concentrated along the spiral arms of our galaxy, where supernova explosions and stellar winds churn the interstellar medium into frothy structures. Some, like the Aquila Rift, form dense curtains that obscure starlight for hundreds of light-years. Others, such as the Chameleon Cloud Complex, serve as stellar nurseries, their gas collapsing into new suns. Our solar system's journey through this evolving landscape means encounters like our current one aren't anomalies, they're inevitable milestones in a galaxy teeming with interstellar weather. The real breakthrough came when astronomers combined radio telescope data with ultraviolet absorption studies. This cross revealed how frequently star systems pass through such clouds, roughly once every 50 to 100,000 years on average. Some crossings last mere centuries, while others, like our impending encounter, may persist for millennia, but frequency alone doesn't predict danger. The most disruptive events likely come from clouds born in particularly violent supernova, which carry not just gas but potent magnetic fields capable of warping planetary magnetospheres. What does this mean for other civilizations across the galaxy? If intelligent life exists elsewhere, it too must navigate these interstellar tides. A species developing spaceflight during their system's passage through a dense cloud might face insurmountable radiation barriers, while others born during quiet interstellar periods could expand effortlessly. This cosmic lottery adds another layer to the Fermi paradox. Perhaps some advanced civilizations aren't silent by choice, but temporarily isolated by the very clouds that fill our galaxy. As telescopes grow more sophisticated, they're spotting even subtler structures, filaments thinner than a human hair stretched across light years, or bubble-like voids where previous clouds have been blown clear by stellar winds. Each discovery refines our predictions for future encounters, helping astronomers create a kind of interstellar weather forecast. the emerging picture is clear. Our galaxy isn't a static backdrop. It's a dynamic ecosystem where star systems like ours surf waves of gas and dust, each passage leaving invisible marks on planets, atmospheres, and perhaps even the evolution of life itself. Right now, teams of astrophysicists are working on something that sounds like science fiction, a cosmic early warning system designed to predict interstellar storms. Think of it like the weather app on your phone, but instead of checking for rain, it scans the galaxy for invisible clouds of gas and dust that could reshape our solar system's defenses. The key lies in a network of observatories, both on Earth and in space, that act as interstellar buoys measuring subtle changes in starlight, tracking shifts in cosmic ray levels, and mapping the magnetic ripples at the edge of our heliosphere. One of the most promising tools in this emerging field is something called interstellar absorption spectroscopy. When light from distant stars passes through an approaching cloud, certain wavelengths get absorbed, leaving behind a unique chemical fingerprint. By analyzing these absorption lines, scientists can determine not just the cloud's composition, but its speed, density, and even the orientation of its magnetic fields. It's like reading the ingredients and velocity of a storm before it reaches your doorstep. Missions like the upcoming James Webb Space Telescope successor, LUVOIR, could take these readings to new heights, spotting clouds decades or even centuries before they arrive. But forecasting isn't just about spotting hazards, it's about preparing for them. Imagine a future where space agencies receive alerts about incoming interstellar weather, much like hurricane warnings today. Satellite operators might adjust orbits to minimize radiation exposure, Mars colonists could stockpile shielding materials, and astronomers might prioritize studies of the heliosphere's changing boundaries. Some researchers even speculate about active defense systems, giant magnetic coils at the solar system's edge, designed to stabilize the heliosphere during intense compression. While that's still theoretical, the principle is clear: knowledge buys time, and time allows adaptation. The challenges are immense. Unlike Earth's atmosphere, where weather follows familiar patterns, interstellar clouds move through a vacuum devoid of friction or predictable currents. Their behavior hinges on variables we're still learning to measure: the twist of magnetic fields, the clash of particle streams, even the gravitational tug of passing stars. That's why projects like the Interstellar Boundary Explorer are so vital. By mapping the flow of energetic neutral atoms at the heliosphere's edge, IBEX creates a real-time snapshot of pressures building against our cosmic shield. Combine that data with supercomputer simulations, and you've got the beginnings of an interstellar forecast model. What makes this endeavor so revolutionary isn't just the technology, it's the shift in perspective. For most of human history, space was seen as an empty, unchanging void. Now we know it's a dynamic ecosystem, filled with currents and structures that influence everything from planetary climates to the feasibility of deep space travel. The same way sailors once relied on wind charts to cross oceans, future explorers might consult interstellar weather maps before venturing beyond the heliosphere. And here's the most fascinating part: we're not just passive observers in this process. Every probe we send into the outer solar system, every telescope we point at the stars, adds another piece to the puzzle. In a way, humanity is weaving its own cosmic safety net, thread by thread, across the vastness of space. The interstellar cloud approaching us isn't just a scientific curiosity. It's the first test of whether we can learn to navigate a galaxy that's far more alive than we ever imagined. Life on Earth has weathered cosmic storms before, but never while we've had the tools to watch it unfold. If the interstellar cloud's pressure compromises our heliosphere, the uptick in cosmic radiation could rewrite the rules for countless species. Picture a forest canopy where trees suddenly face higher mutation rates in their seeds, or ocean currents where plankton, the foundation of marine food webs, absorb more radiation than they have in epochs. These changes wouldn't happen overnight, but over generations, subtle shifts could ripple through ecosystems, testing the resilience of life itself. Take migratory species like sea turtles or songbirds, which navigate using Earth's magnetic field as their compass. Cosmic rays don't just carry energy, they distort the very magnetic signatures these animals rely on. A weakened heliosphere might allow more of these particles to reach our planet's magnetosphere, scrambling nature's GPS. Imagine hatchling turtles veering off course because the magnetic cues they've followed for millions of years suddenly flicker like a faulty streetlight. Or consider the Arctic tern, whose pole-to-pole journey depends on precise magnetic readings. Even minor disruptions could force these travelers to adapt their routes or face collapse in populations already stressed by climate change. But the real wild card lies in the microscopic world. Radiation-induced mutations aren't inherently bad. They are also the raw material for evolution. Some bacteria and plants might thrive under these conditions, developing repair mechanisms or even harnessing the extra energy. Lichens, for instance, already survive in space's harsh radiation during orbital experiments. Could future forests harbor trees with bark that absorbs and neutralizes cosmic rays? Or might deep-sea extremophiles, already adapted to high-pressure darkness, find new advantages in a slightly more radioactive ocean? The irony is profound. The same forces that threaten some species could unlock evolutionary innovations we can't yet imagine. Earth's atmosphere remains a formidable secondary shield, absorbing most radiation before it reaches the surface. Yet even small leaks matter over geological time. High-altitude ecosystems, from alpine flowers to Andean condors, would face the brunt of any increase. Scientists studying ancient pollen records have found evidence of past radiation spikes correlating with shifts in plant diversity, suggesting that while life persists, its cast of characters might change. And then there's the invisible chemistry. Cosmic rays ionize air molecules, potentially altering ozone layers or cloud formation patterns in ways that could cool or warm regions unpredictably. The deeper lesson here isn't doom, it's adaptability. Life has survived supernova, asteroid impacts, and ice ages by bending without breaking. This interstellar encounter is another test in a long cosmic gauntlet, one that might favor species with hidden strength. Perhaps the descendants of today's tardigrades, microscopic water bears that withstand extreme radiation, will inherit Earth's next chapter. Or maybe humans will apply our unique tool, foresight, using genetic engineering or radiation-shielded habitats to tilt the odds. Either way, the cloud's approach isn't just an astronomical event. It's a slow-motion experiment in how life responds when the universe turns up the heat. Our satellites, power grids, and global communications networks form an invisible web that modern civilization depends on, but this technological safety net might be far more fragile than we realize. Floating in the void beyond Earth's atmosphere, satellites face constant bombardment from cosmic rays and solar particles, threats normally softened by the heliosphere's protective buffer. If that shield weakens, even temporarily, the consequences could cascade through every smartphone call, GPS navigation signal, and weather forecast. Solar storms, which already pose risks to electronics, could become more frequent or intense, their charged particles flooding into systems never designed to handle such surges. Transformers in power grids, for instance, might overheat and fail under increased geomagnetic stress, triggering blackouts that ripple across continents. The real danger lies in the compounding effects. A single powerful solar flare during heightened cosmic ray exposure could fry sensitive satellite components while simultaneously disrupting the ionosphere, scrambling radio signals essential for aviation and emergency services. Imagine a scenario where astronauts on the Moon or Mars lose contact with Earth because the relay satellites linking them malfunction. Or consider financial markets where stock trades timed to the millisecond could glitch as cosmic rays flip bits in supercomputers. These aren't theoretical risks. Similar disruptions have already occurred on smaller scales. In 1989, a solar storm blacked out Quebec's power grid for 9 hours, while in 2003, another damaged over a dozen satellites in what scientists now call the Halloween storms. With a compromised heliosphere, such events might transition from rare emergencies to recurring challenges. Protecting this infrastructure demands innovation on multiple fronts. Engineers are already testing new satellite designs with self-healing chips that automatically reset after radiation hits, and power grids are incorporating superconducting materials to dampen electromagnetic surges. Perhaps the most promising frontier is quantum technology, encryption methods, and computing architectures inherently resistant to cosmic ray interference. Meanwhile, space agencies are developing early warning systems that could give power plants and satellite operators precious minutes to switch to shielded backups before a solar storm arrives. The irony is striking. Humanity's greatest technological achievements might soon need shielding from the same cosmic forces that shaped Earth's evolution. This interstellar cloud could become the catalyst for a new era of resilient engineering, pushing us to reinvent everything from microchips to megacities. The solutions won't just safeguard our present, they'll define how we explore the stars beyond a changing heliosphere. Some media outlets love to paint this interstellar cloud as a doomsday scenario, a looming cosmic catastrophe that'll fry our electronics, mutate our DNA, or worse. But let's take a breath and unpack what's really happening, because the truth is far more fascinating than fiction. One of the biggest myths that this cloud will hit Earth like some kind of space tsunami. In reality, it's more like walking through a fog bank so diffuse you might not even notice, with particles spread so thin they'd make the vacuum of space seem crowded by comparison. The real interaction happens at the edges of our solar system, where the heliosphere acts like a sieve, not a solid wall. Then there's the fear that cosmic rays will suddenly spike to lethal levels. While it's true the heliosphere blocks a significant portion of these high-energy particles, Earth has its own defenses, a magnetic field and thick atmosphere that have shielded life for billions of years. Even if the heliosphere weakens, the increase in radiation at ground level would likely be subtle, something scientists would measure with sensitive instruments rather than something we'd feel. Think of it like sunscreen wearing off slightly on a cloudy day. You might get a tiny bit more UV, but you're not instantly burning. Another common exaggeration. That the cloud will trigger immediate climate chaos. While cosmic rays can influence cloud formation in theory, the effect is hotly debated and far from apocalyptic. Earth's climate is shaped by countless factors, from ocean currents to greenhouse gases. This interstellar visitor would be a whisper in that storm. Historical encounters, like the one hinted at in ice cores from 2 million years ago, show no evidence of abrupt climate collapses. Instead, they reveal a planet adapting to subtle cosmic nudges, not buckling under them. Perhaps the most persistent myth is that this cloud is some kind of alien anomaly, a mysterious thing invading our solar system. In truth, these clouds are as natural as the solar wind itself, remnants of stars that lived and died long before our sun ignited. They're not rare, not sinister, and certainly not targeted at us. The galaxy is full of them, each a scrap of the universe's recycling program, carrying elements forged in stellar furnaces. So why the hype? Part of it's the allure of disaster narratives. They grab attention in ways nuanced science often doesn't. But the real story here isn't about danger, it's about discovery. This cloud offers a once-in-millennia chance to study how solar systems interact with the galaxy, a process that's shaped life's evolution more than we've realized. Instead of fearing the unknown, we're learning to read it one cosmic whisper at a time. Tracking this interstellar cloud isn't just a job for a handful of elite astronomers. It's a global challenge that demands eyes across continents and expertise from every corner of science. Space agencies like NASA and ESA are already pooling data from their deep space probes, while university labs from Tokyo to Cape Town calibrate instruments to detect the cloud's faintest whispers. But here's the game changer. Modern technology lets anyone with a backyard telescope or even a smartphone join the hunt. Citizen science platforms like Zooniverse now host projects where amateur astronomers can analyze stellar spectra for telltale absorption lines, the same subtle clues that first revealed the cloud's approach. Imagine a retired teacher in Norway or a high school student in Chile spotting a crucial data point that professionals missed. That's the power of collective observation. The beauty of this collaboration lies in its diversity. Professional observatories track the cloud's broad movements with radio telescopes stretching hundreds of feet across, while amateur networks fill in blind spots with countless smaller observations. Together, they create a mosaic no single institution could achieve. Take the American Association of Variable Star Observers, where volunteers have contributed over 40 million celestial measurements since 1911. Their meticulous records helped confirm the cloud's trajectory by comparing how its gases dim the light of background stars over decades. This isn't just busy work, it's foundational science, built on the combined patience of generations. Beyond astronomy, the effort bridges disciplines in unexpected ways. Atmospheric physicists normally focused on Earth's climate are modeling how increased cosmic rays might ionize our upper atmosphere, while marine biologists contribute insights from radiation-resistant deep-sea microbes that could hint at evolutionary adaptations. Even historians play a role, scouring ancient texts for accounts of unusual celestial events that might reveal past heliosphere encounters. The cloud's approach has become a rare unifying focus, proving that cosmic phenomena don't respect academic silos, they demand we break them down. Perhaps the most innovative partnerships emerge from open data initiatives. When NASA IBEX mission released its heliosphere maps to the public, coding boot camps and university hackathons spontaneously produced visualization tools that professional scientists now use daily. One team even developed an AI model that predicts magnetic field interactions by training on both spacecraft data and amateur radio observations of cosmic noise. These collaborations thrive because the stakes transcend borders. The cloud doesn't care about nationality or funding disputes. Its story belongs to anyone willing to look up and wonder. The challenge now is sustaining this momentum as the encounter unfolds over centuries. Unlike quick cosmic events like solar eclipses, monitoring the cloud's effects requires institutional memory spanning generations. Some propose a global interstellar watch program, embedding cloud tracking into school curricula and creating digital time capsules so today's findings inform future researchers. Others advocate for standardized data protocols so observations from different eras remain comparable. The goal isn't just preparation, it's legacy. By weaving this effort into humanity's collective knowledge, we ensure that when the cloud's influence peaks, whether in 50 years or 500, the world won't be starting from scratch but building on foundations we lay today. What makes this collaboration extraordinary isn't just the science, it's the reminder that in the face of cosmic forces, our best tool has always been each other. From the first astronomers who charted stars on clay tablets to the teams now launching probes beyond the solar system, curiosity thrives when shared. The interstellar cloud isn't just approaching Earth, it's bringing humanity together in ways we're only beginning to understand. As this interstellar cloud drifts closer, its potential effects don't just raise scientific questions, they force humanity to confront profound ethical dilemmas. Picture a future where increased cosmic radiation demands radical choices. Do we invest billions in shielding Earth's atmosphere or prioritize off-world colonies as a planetary backup? Should we alter crops to withstand higher radiation levels, or would that set a precedent for genetic tinkering we can't reverse? These aren't hypotheticals, they're decisions that could redefine our relationship with nature, technology, and even what it means to be human. The debate begins with resource allocation. If the heliosphere weakens over centuries, protecting vulnerable populations from radiation exposure might require massive infrastructure. Think atmospheric scrubbing towers or underground cities. But with finite global budgets, every dollar spent on cosmic defense could mean less funding for healthcare, education, or climate adaptation. Who gets priority? Nations with space programs might advocate for off-world solutions like orbital sunshades, while developing countries could argue for immediate Earth-based protections. The tension mirrors current climate justice struggles, but with an interstellar twist. When the threat comes from beyond our solar system, does responsibility fall equally on all nations or disproportionately on those with the technology to intervene? Space colonization adds another layer. If Earth becomes marginally less hospitable, Mars or lunar bases might shift from exploration outposts to vital insurance policies. But this raises uncomfortable questions about who gets access. Would off-world havens become enclaves for the wealthy, leaving billions behind on a changing Earth? History suggests survival technologies often widen inequality. Consider how early vaccines or flood barriers favored certain populations. Ethical frameworks from philosophers like John Rawls argue for equitable distribution of risks and resources, but applying those principles to interstellar challenges would require unprecedented global cooperation. Then there's the biological frontier. Scientists already experiment with radiation-resistant genes in microorganisms and crops. Scaling this to humans, say, enhancing DNA repair mechanisms, could safeguard future generations, but at what cost? Bioethicists warn of slippery slopes. Once we edit genomes for cosmic adaptation, where do we draw the line? And if only some nations embrace genetic modifications, could humanity splinter into subspecies with unequal cosmic resilience? These questions echo past debates over human enhancement, but with higher stakes, the very survival of our species in an altered heliosphere. The heart of these dilemmas lies in balancing precaution with progress. Overreacting to a slow-moving threat could divert resources from more immediate crises, while underreacting might leave civilizations unprepared for cascading effects. Ancient societies faced similar choices when building flood walls or grain stores, weighing present costs against future survival. But unlike our ancestors, we have tools to model long-term scenarios and democratize decision-making. Citizen assemblies, AI-powered policy simulations, and interstellar impact assessments could help navigate these trade-offs transparently. What makes this moment unique isn't just the scale of the challenge, it's the opportunity to set ethical precedents for cosmic citizenship. The choices we make today, from radiation-hardened infrastructure to inclusive space policies, will echo across millennia. They'll determine whether humanity responds to interstellar threats with division or solidarity, short-term fixes or generational wisdom. The cloud approaching us isn't just a physical phenomenon, it's a mirror, reflecting back the values we'll need to thrive in a universe far more dynamic than we ever imagined. The approaching interstellar cloud forces us to think beyond temporary fixes. It demands a radical reimagining of how humanity safeguards its future in an ever-changing cosmos. One audacious idea gaining traction among astrophysicists is heliosphere engineering, actively reinforcing our solar system's protective bubble against external pressures. Picture vast magnetic sails deployed at the heliosphere's edge, designed to stabilize its boundary like invisible breakwaters against an interstellar tide. These theoretical megastructures would harness the sun's own energy, using superconducting loops to amplify and extend our natural magnetic defenses. While still in conceptual stages, recent breakthroughs in plasma physics and nanotechnology suggest such feats might be achievable within centuries, a blink in cosmic time. The challenges are staggering. Unlike Earth's atmosphere, which we can manipulate with relative precision, the heliosphere operates on scales that dwarf human engineering. Its boundary fluctuates across billions of miles, responding to forces no terrestrial structure has ever faced. Yet researchers point to natural analogs for inspiration. Jupiter's magnetosphere, for instance, stretches so far that it periodically brushes Saturn's orbit, demonstrating how planetary magnetic fields can dominate vast regions of space. Could we create artificial versions of these cosmic shields? Projects like NAS, a solar cruiser, a spacecraft propelled by a solar sail, hint at the first steps, proving we can harness space's invisible forces for navigation. Scaling this up to heliosphere defense would require materials stronger than graphene and energy sources rivaling small stars, but the physics doesn't forbid it, only our current technology does. Meanwhile, the cloud's long timeline presents an unexpected opportunity: the chance to develop interstellar migration as a viable survival strategy. Generational ships, once confined to science fiction, are now serious subjects at institutions like the Breakthrough Starshot Initiative. Their proposed light sail probes could reach Alpha Centauri in decades, paving the way for larger vessels. The key lies in closed-loop ecosystems and propulsion systems that don't rely on Earth-bound resources. Imagine self-sustaining arcs carrying frozen embryos or artificial wombs, not as replacements for Earth, but as backups should our home system become inhospitable. Recent experiments with algae-based air purification and mycelium-based construction materials on the International Space Station prove we're already laying groundwork for these nomadic habitats. What makes this moment pivotal is the intersection of necessity and innovation. Past civilizations faced existential threats like ice ages or supervolcanoes with no alternatives but adaptation. We're the first generation that might engineer escape routes, whether through shielding our solar system or expanding beyond it. The cloud becomes a catalyst, accelerating timelines for technologies that could also defend against nearer-term dangers like asteroid impacts or nearby supernova. Some argue this cosmic nudge is providential. Without such challenges, humanity might have remained complacent on Earth until disaster struck. Yet these grand visions must be tempered with ethical pragmatism. Diverting resources to interstellar projects could strain societies already grappling with inequality and climate crises. There's also the haunting question of who gets left behind if off-world havens become reality. Philosophers like Nick Bostrom suggest establishing ethical frameworks now, perhaps through a cosmic conservation treaty that treats space expansion as a collective human heritage rather than a competitive race. The deeper lesson transcends any single technology. This interstellar encounter reminds us that survival isn't just about enduring change, it's about anticipating it across generations. Whether through engineering our celestial backyard or planting seeds among the stars, we're being called to think like a multi-millennial civilization. The cloud's approach isn't just a scientific event, it's the universe handing us a pop quiz on long-term thinking. And for the first time in history, we're beginning to sketch answers in the margins of the cosmos. This interstellar cloud isn't just a scientific curiosity, it's a cosmic classroom, offering the next generation a front-row seat to one of the universe's most profound lessons. Change is the only constant. For a child gazing at the stars tonight, this isn't some abstract concept in a textbook. It's a real-time demonstration that space isn't a static backdrop, but a dynamic, evolving frontier where discoveries unfold across human lifetimes. Imagine a middle schooler tracking the cloud's progress through citizen science projects, watching as their own observations contribute to humanity's understanding of the heliosphere. That's the kind of hands-on inspiration that transforms casual curiosity into lifelong passion. Teachers and mentors have a golden opportunity here. Instead of presenting astronomy as a series of solved equations, they can frame it as a living puzzle, one where students might someday fill in the blanks. Take the cloud's magnetic fields. We still don't fully understand how they'll interact with our solar system. Could a high school physics class simulate different scenarios using simple magnets and plasma chambers? Or consider the biological implications? Science fairs could explore how extremophiles like tardigrades might adapt to increased cosmic radiation, blending astronomy with biochemistry in ways that spark interdisciplinary thinking. The key is making these connections tangible. When a student builds a model heliosphere out of foam balls and string, they're not just memorizing facts, they're internalizing the scale and fragility of our cosmic neighborhood. Museums and planetariums are already seizing this moment, with interactive exhibits letting visitors pilot a virtual spacecraft through the cloud's predicted path. These experiences don't just educate, they instill something deeper, a sense of ownership over humanity's cosmic journey. But inspiration shouldn't stop at the classroom door. Imagine documentaries that follow the cloud's journey like a celestial David Attenborough narration, or video games where players navigate a shifting heliosphere to protect Earth from radiation surges. Even social media can play a role. Astronomers could live stream data from observatories, turning complex spectral analyses into collaborative detective stories where followers help spot anomalies. The goal isn't just to teach facts, but to cultivate a mindset. Space isn't something distant and untouchable. It's a realm where every curious mind has a role to play. For young women and underrepresented groups in STEM, this moment holds special significance. The scientists leading cloud research today, like Dr. Merav Ofer, whose groundbreaking heliosphere models reshaped the field, are living proof that space exploration isn't confined to any one background. Mentorship programs linking students with researchers studying the cloud could demystify careers in astrophysics, showing that groundbreaking discoveries often begin with simple questions. What if? Why not? The most powerful lesson this cloud offers might be its timeline. Unlike fleeting astronomical events, its effects will unfold over centuries, meaning today's students could become the scientists who monitor its peak impact or the engineers who design solutions to mitigate its effects. That long arc turns abstract concepts like legacy into something visceral. A seventh grader sketching spacecraft designs today might see their grandchildren walk on Mars protected by technologies born from their childhood wonder. Ultimately, this interstellar visitor reminds us that science isn't just about answers, it's about learning to ask better questions. When a teenager looks up at the night sky knowing an invisible force is slowly reshaping our solar system, they're not just seeing points of light. They're witnessing a story still being written, one their generation will help tell, and that's the most thrilling invitation of all. Long before telescopes confirmed its approach, the interstellar cloud was already taking shape in human imagination, not through data points, but in the brushstrokes of painters and the metaphors of poets. Science fiction authors have woven its arrival into apocalyptic tales and transcendent visions for decades, from Arthur C. Clarke's haunting descriptions of cosmic fog in The Songs of Distant Earth to modern graphic novels depicting heliospheric storms as celestial dragons. These creations do more than entertain, they bridge the gap between abstract astrophysics and visceral human experience. When a filmmaker visualizes the heliosphere crumpling like parchment in a cosmic wind, or a composer translates magnetic field oscillations into symphonic movements, they're not just interpreting science, they're giving audiences emotional anchors to grasp the universe's scale. Consider how artists responded when Voyager crossed the heliopause in 2012. While scientists analyzed particle density graphs, musicians like Duran Duran turned the event into album themes, and installation artists projected real-time heliosphere data onto building facades as pulsing light sculptures. This cultural alchemy transforms numbers into narratives, making the invisible tangible. A teenager who might glaze over at a lecture on plasma physics could have their perspective shifted forever by a viral TikTok animation showing Earth's magnetosphere as a shimmering force field battling interstellar winds. Cloud's gradual approach offers a unique canvas for collaborative storytelling across generations. Indigenous star lore, like the Maori tale of Ranginui, the Sky Father separating from Papatuanuku, the Earth Mother, could find new resonance as allegories for the heliosphere's coming trial. Contemporary painters might layer ultraviolet absorption spectra into traditional landscape techniques, creating works that evolve as new data emerges. Already, platforms like NASA's art program are pairing astronomers with ceramicists and holography artists to reinterpret IBEX mission findings as tactile experiences. But art's greatest power may lie in fostering collective resilience. During the Cold War's nuclear anxiety, post-apocalyptic fiction helped societies process existential dread. Similarly, the Cloud's multi-century timeline invites creatives to explore not just catastrophe, but adaptation novels following families across generations as they engineer radiation-resistant crops, or fashion designers prototyping chic magnetic shielding for future Mars colonists. Video games could simulate the ethical dilemmas of heliosphere engineering, turning players into cosmic problem solvers. Perhaps most crucially, artists can challenge the narratives we inherit. While headlines warn of cosmic threats, a muralist might depict the cloud as a celestial midwife, bringing new elements to seed future star systems. A poet could reframe our shrinking heliosphere not as loss, but as the universe drawing Earth into a tighter embrace. These perspectives don't contradict science, they expand its emotional vocabulary, helping civilizations navigate change not just with calculators, but with wonder. The cloud's true lesson might be this: the equations predicting its path tell only half the story. The rest unfolds in the songs we write about dark skies, the children's books explaining cosmic rays with friendly particle characters, the augmented reality exhibits letting visitors touch interstellar gas. As the boundary between our solar system and the galaxy blurs, so too does the line between observer and participant. Every painting, every melody, every myth becomes part of humanity's answer to the cosmos' silent question: how will you meet the unknown? History shows us that the universe delights in defying expectations just when we think we've mapped its boundaries. it reveals new layers of complexity. The interstellar cloud approaching our solar system is no exception. Despite our most sophisticated models, there's an undeniable truth: space has a way of surprising us. Remember when Voyager 1 first crossed into interstellar space, scientists expected a clean boundary, but instead found a frothy, magnetic foam no one had predicted. Or consider the Oumuamua asteroid. What astronomers initially assumed was a simple space rock turned out to exhibit properties so unusual, some still debate its origins. These weren't failures of science, but reminders that the cosmos operates on scales and principles we're only beginning to grasp. Adapting to this uncertainty requires more than just better telescopes. It demands a fundamental shift in how we approach discovery. Traditional scientific methods often seek definitive answers, but the interstellar cloud invites us to embrace iterative learning. Think of it like navigating a foggy shoreline. Each new datum is a faint buoy light, revealing small stretches of the path ahead without ever showing the entire coast. Space agencies are already adopting this mindset. NASA Interstellar Mapping and Acceleration Probe, launching later this decade, isn't just designed to observe, it's built to evolve, with software that can be updated as we uncover new questions about the cloud's behavior. Technologically, resilience means designing systems that can pivot when the unexpected arrives. Satellite manufacturers are experimenting with modular components that can be swapped remotely when radiation exposure increases, while AI-driven telescopes are learning to recognize and flag anomalies that don't fit existing models. The European Space Agency's upcoming Comet Interceptor mission embodies this philosophy. It won't even select its target until after launch, waiting for an interstellar visitor to reveal itself. This isn't just practical, it's a philosophical breakthrough in space exploration, acknowledging that some discoveries can't be scheduled. Socially, the challenge is deeper. Human brains crave certainty, yet cosmic phenomena operate on timelines that dwarf individual lifespans. How do we maintain public engagement and funding for research that may not yield definitive answers for centuries? Museums are experimenting with immersive exhibits that visualize the cloud's slow approach in accelerated time, while educators are reframing uncertainty not as a weakness, but as an invitation to participate. Citizen science initiatives like Galaxy Zoo have shown that ordinary people can make extraordinary contributions when given the right tools. A lesson now being applied to heliosphere research through platforms where volunteers classify interstellar gas patterns. The cloud's greatest gift may be the humility it instills. Ancient navigators learned to sail by accepting that winds change and stars shift, not as obstacles but as essential parts of the journey. Similarly, embracing cosmic uncertainty doesn't mean abandoning preparation. It means preparing to be surprised. Future generations may look back on this era not for the predictions we got right, but for how we cultivated the curiosity and flexibility to meet whatever the universe revealed. After all, the unknown isn't a barrier, it's the frontier where discovery begins. Our solar system isn't unique in its journey through the galaxy's shifting tides. Countless other stars are also navigating their own interstellar weather. Astronomers have turned their telescopes toward exoplanetary systems, searching for telltale signs of heliospheres under pressure. The results are both reassuring and humbling. Around the young star Beta Pictoris, just 63 light-years away, the Hubble Space Telescope detected vast rings of dust warped into strange shapes, evidence of a recent collision with an interstellar cloud that likely compressed its protoplanetary disk. Meanwhile, observations of the TRAPPIST-1 system reveal its 7 Earth-sized planets bathed in stellar winds far weaker than our Sun's, suggesting their tiny red dwarf star struggles to maintain a robust protective bubble. These cosmic snapshots reveal a universal truth. No solar system exists in isolation. Some worlds face far harsher conditions than Earth ever will. Take HD 21934b, a scorching exoplanet orbiting so close to its star that its atmosphere is literally evaporating into space. For this doomed world, an incoming interstellar cloud might be the least of its worries. On the other end of the spectrum, rogue planets, those flung from their star systems, wander the galaxy naked to cosmic rays, their frozen surfaces bombarded by unfiltered interstellar radiation. Yet even these extreme examples hint at life's potential resilience. Subsurface oceans on rogue planets could theoretically harbor microbes adapted to high radiation, just as Earth's deepest dwelling organisms thrive in places sunlight never reaches. The real surprises come from systems that defy our expectations. Around the pulsar PSRB 1257+12, planets orbit the corpse of an exploded star, enduring magnetic fields trillions of times stronger than Earth. These worlds have survived supernova that vaporized lesser planets, proof that celestial bodies can adapt to conditions we'd consider unsurvivable. Their existence suggests that given enough time and the right evolutionary paths, life might find ways to persist even when interstellar clouds dramatically reshape a solar system's defenses. What makes Earth's situation remarkable isn't our vulnerability, it's our timing. We're privileged to exist during a period when our solar system's protective bubble remains robust enough to foster complex life, yet transparent enough for us to study the approaching cloud. This cosmic sweet spot allows us to prepare in ways other civilizations might not have managed. Ancient Martian microbes, if they ever existed, likely had no warning before their planet's magnetic field collapsed and its atmosphere eroded. We, by contrast, can track our interstellar weather forecast centuries in advance, a gift of foresight that might prove vital as we navigate the galaxy's ever-changing currents. The deeper lesson from these distant systems isn't about doom, it's about diversity. Just as Earth's biosphere thrives from deserts to deep sea vents, the galaxy teems with solar systems in every conceivable state of adaptation. Some huddle behind feeble stellar winds, others bask in the protection of massive stars. A few might even harness their interstellar clouds creatively, using compressed heliospheres to trap cosmic rays as an energy source, or cultivating radiation-resistant life forms in their shadows. As we watch our own interstellar visitor approach, these exoplanetary examples don't just teach us what to fear, they expand our imagination for what's possible when a solar system and a cloud meet. The interstellar cloud drifting toward our solar system does more than challenge our understanding of cosmic weather. It casts a haunting shadow over one of astronomy's greatest mysteries, the Fermi paradox. If the universe is so vast and ancient, why haven't we encountered other civilizations? The answer might lie in these very clouds. Imagine a galaxy where intelligent life repeatedly blossoms, only to have its technological progress erased when its protective heliosphere buckles under interstellar pressure. Cosmic rays flood in, crippling electronics, mutating DNA, and forcing societies back to pre-industrial survival. It's a chilling solution to the paradox, not because civilizations are rare, but because the galaxy itself acts as a recurring filter, resetting the clock with each passing cloud. Consider the timing. Complex life on Earth took billions of years to evolve, with humanity's technological era occupying a mere blink in cosmic terms. If interstellar clouds compress heliospheres every few 100,000 years, a geological heartbeat, the window for a civilization to develop radio telescopes or spacecraft, might close before they ever detect others. Planets in the Milky Way's spiral arms, where these clouds cluster, could face this cycle relentlessly. their histories might resemble a staircase where each step forward is met with a cosmic hand pushing them back down. This isn't pure speculation. Geological records show past periods when Earth radiation exposure spiked, some aligning with suspected heliosphere compressions. While life endured, these events correlate with extinction waves and evolutionary bottlenecks, now project that across the galaxy, a planet where intelligent dinosaurs built primitive cities before a cloud-induced radiation surge, an aquatic civilization on an ocean world whose delicate electronics fried during a millennia-long cosmic ray storm. The ruins of these societies wouldn't just be buried, they'd be erased, their metals corroded, their silicon chips reduced to sand. Yet there's an ironic twist. The same clouds that might stifle technological civilizations could also be essential for life's origins. These interstellar wanderers deliver heavy elements like iron and carbon, the building blocks of planets and biology. They're both midwives and executioners, providing the ingredients for life while periodically culling its most ambitious creations. This duality reshapes how we view the Fermi paradox. Instead of asking, "Where is everybody?" we might ask, "How many have been silenced?" and wonder if Earth's quiet corner of the galaxy, with its relatively stable heliosphere, is less a typical habitat than a cosmic sanctuary. Perhaps most unsettling is the implication for humanity's future. If this hypothesis holds, our current technological explosion coincides with a rare lull in interstellar weather. The cloud approaching us might not just be a scientific curiosity. It could be the first test of whether any civilization can outthink the galaxy's cycles. Will we find ways to reinforce our heliosphere or scatter self-repairing probes as backups? Or will we, like so many others before us, become another silent entry in the universe's unread ledger? The answers won't just solve a paradox, they'll define whether intelligence is a fleeting spark or a flame that can outlast the cosmic winds. While Voyager 1 and 2 gave us our first taste of interstellar space, they were never designed to study an approaching cloud. They stumbled into the unknown like pioneers without maps. Future missions, however, are being crafted with purpose, armed with instruments sensitive enough to read the interstellar medium like a cosmic fingerprint. At the forefront is NAS, an interstellar mapping and acceleration probe, or IMAP, set to launch in 2025. Unlike its predecessors, IMAP won't just drift through the boundary, it'll park itself at Lagrange Point 1, a gravitational sweet spot a million miles sunward of Earth, where it can act as a high-precision monitor for incoming interstellar particles. Its suite of sensors includes advanced energetic neutral atom imagers, which don't just detect particles but reconstruct their paths backward, like tracing raindrops to the storm that birthed them. But decoding the cloud's secrets demands more than remote sensing. The European Space Agency's proposed Comet Interceptor mission, while primarily aimed at studying pristine comets, carries ultraviolet spectrometers capable of analyzing the cloud's composition in unprecedented detail. By measuring how starlight filters through the cloud's outermost tendrils, these instruments could reveal the precise mix of hydrogen, helium, and trace metals, essentially taking the cloud's temperature and blood pressure before it reaches us. Meanwhile, private initiatives like Breakthrough Starshot's nanocraft, though designed for interstellar travel, might serve as nimble scouts. Imagine swarms of gram-scale probes, each equipped with miniature magnetometers and plasma wave detectors, darting through the cloud's turbulence like bees mapping a garden. The real game-changer could be a dedicated interstellar probe, something like NAS, a conceptual interstellar probe, designed to plunge directly into the cloud's heart. Unlike Voyager's jury-rigged instruments, this mission would carry purpose-built tools, Faraday cups to measure electric fields in the cloud's ionized gases, dust analyzers weighing individual atoms, and perhaps most crucially, a magnetometer array capable of untangling the cloud's magnetic spaghetti. These readings would settle debates about how interstellar fields interact with our heliosphere, whether they slip past like two combs intertwining or clash in violent reconnection, events that ripple inward. Yet the greatest insights might come from an unexpected source, gravitational wave detectors. While LIGO and its successors were built to study colliding black holes, their ultrasensitive lasers could potentially detect subtle space-time distortions caused by the cloud's immense but diffuse mass. It's a long shot, but if successful, it would mark the first time we've weighed an interstellar structure directly, rather than inferring its presence from absorbed starlight. What unites these missions isn't just technology, it's philosophy. Where Voyager was a message in a bottle, these probes are active listeners, designed not just to endure the interstellar environment but to converse with it. The data they return won't just fill textbooks, it'll rewrite our definition of local space, revealing a solar neighborhood far more dynamic and interconnected than we ever imagined. After all, the cloud isn't just approaching, it's inviting us to see the galaxy not as a void but as a living, breathing entity. And for the first time in history, we're ready to accept the invitation. The interstellar cloud drifting toward our solar system isn't just a scientific phenomenon, it's a mirror held up to humanity's deepest questions about meaning and agency in an indifferent universe. For centuries, we've viewed cosmic events as forces beyond our influence, like ants observing the turning of seasons. But this encounter shatters that passive perspective, demanding we ask, does intelligence grant us the right, or perhaps the responsibility, to become stewards of our cosmic neighborhood? Ancient stargazers tracked celestial movements to predict floods and plant crops. Future generations might manipulate those very forces to safeguard civilization. The cloud forces this evolution from observers to architects. Consider the philosophical shift this represents. Most cultures frame their place in the cosmos through mythologies of submission, whether to capricious gods or the relentless laws of physics. The Norse saw the sky as Ymir's skull. The Maori attribute earthquakes to the Earth Mother stirring in her sleep. Even modern science often presents humanity as incidental, a fleeting spark in an unfathomably vast universe. Yet the approaching interstellar cloud offers an alternative narrative, one where consciousness becomes a cosmic variable. By contemplating how to preserve our heliosphere, we're not just reacting to nature, we're beginning to negotiate with it. This moment echoes pivotal transitions in human thought. The agricultural revolution transformed us from passive foragers to active cultivators. The scientific revolution replaced superstitious fatalism with empirical agency. Now, heliosphere engineering could mark a third great pivot, the moment we stop merely enduring our cosmic environment and start curating it. Some ethicists argue this crosses a dangerous threshold, likening it to playing God. Others counter that all intelligence naturally progresses from adapting to environments to shaping them, whether through building shelters or terraforming planets. The cloud's slow approach gives us time to debate these boundaries, a rarity in human history where existential threats usually demand instant response. What makes this reflection urgent isn't just theoretical, it's practical. Unlike earthquakes or solar flares, this interstellar event unfolds across generations, requiring unprecedented continuity of knowledge and purpose. Ancient Egyptian architects planned pyramids knowing they'd never see completion. Cathedral builders laid foundations for descendants to finish. Modern societies, with their quarterly earnings reports and election cycles, struggle with such long horizons. The cloud challenges us to resurrect these ancestral patience muscles while wielding tools our predecessors couldn't imagine. Can democracies maintain interstellar policies across centuries? Will corporations invest in infrastructure whose benefits won't materialize for 500 years? Perhaps most profoundly, the cloud redefines what it means to be a civilization. Historians measure societies by art, wars, or technological leaps, but future scholars might judge ours by whether we recognized our solar system as an integrated system worth maintaining. In this light, protecting the heliosphere becomes more than engineering. It's a cultural milestone, like the first cities or spaceflights. The Lakota phrase, "Mitakui Oyasin," all my relations, traditionally encompassed living things. Soon, it might include magnetic fields and solar winds as kin we nurture. This perspective transforms the cloud from threat to teacher. Its silent approach whispers that intelligence isn't just about solving immediate problems, but about tending to systems whose rhythms outlast species. The dinosaurs ruled for 160 million years, yet left no cosmic legacy beyond fossils. We who have barely existed for a geological blink now face a choice. Will we be the first Earthlings to extend our care beyond the atmosphere? Or will we remain prisoners of short-term thinking until the universe washes us away? The answer won't just determine our survival, it'll define what survival even means in a cosmos where stardust thinks. The interstellar cloud drifting toward our solar system has sparked sensational headlines predicting everything from mass extinctions to technological collapse. But the reality is far more nuanced than doomsday scenarios suggest. Yes, this cosmic visitor will reshape our heliosphere over centuries, but not with the sudden devastation of an asteroid impact or solar superflare. Think of it more like climate change than an explosion, a slow, measurable shift that gives humanity generations to adapt and innovate. Scientists monitoring the cloud's trajectory compare its effects to a gentle tide lapping at a shoreline, gradually reshaping the coast over lifetimes rather than erasing it in an instant. What gets lost in alarmist narratives is the cloud's true scientific value. This isn't just a potential hazard, it's a once-in-millennia opportunity to study how solar systems interact with the galaxy's interstellar medium. Imagine having front-row seats to a process that shaped planetary environments across cosmic history, from the birth of Earth's atmosphere to the evolution of life itself. By fixating on catastrophe, we risk overlooking the profound insights waiting to be uncovered. How magnetic fields dance at the heliosphere's edge, how cosmic rays filter through shifting barriers, even how life might harness these changes to evolve in unexpected directions. Communicating this balance requires grounding the science in relatable metaphors. The heliosphere isn't a rigid shield that will suddenly shatter. It's more like a living membrane that breathes and flexes with external pressures. Just as your skin protects you from germs while still allowing touch and temperature signals to pass through, a compressed heliosphere might let in slightly more cosmic rays without leaving Earth defenseless. Our planet's own magnetic field and thick atmosphere provide backup protection, like a nested set of filters catching what the outer layer misses. Even during past periods when Earth's heliospheric defenses weakened, evidenced by ice core isotopes, life not only survived but diversified, suggesting resilience is baked into our biosphere. The key lies in distinguishing between disruption and doom. Satellite operators might need to upgrade radiation shielding over decades, and future Mars colonists could face higher radiation exposure. But these are engineering challenges, not existential threats. Humanity has already tackled comparable hurdles, from adapting to fluctuating ozone layers to hardening power grids against solar storms. The cloud's slow approach gives us an advantage our ancestors never had: time to test solutions through simulations, prototype technologies, and share knowledge globally. Perhaps the most overlooked aspect is how this event reframes our relationship with the cosmos. For too long, space has been portrayed as either a passive backdrop or a source of apocalyptic danger. The interstellar cloud invites a third perspective, one where we engage with the universe as active participants, learning its rhythms and adapting to its ebbs and flows. That shift isn't just practical, it's philosophical. By moving beyond doomsday dichotomies, we open ourselves to a richer dialogue with the stars, one where curiosity and preparedness walk hand in hand toward a future we're only beginning to imagine. Knowledge about the interstellar cloud shouldn't be locked away in academic journals or confined to scientific conferences. It belongs to everyone. Imagine a farmer in Kenya checking her smartphone for interstellar weather updates alongside the daily forecast, or a high school student in Brazil exploring the cloud's trajectory through an interactive VR simulation. This isn't just about spreading facts, it's about empowering people to see themselves as part of a cosmic story unfolding in real time. The challenge lies in bridging the gap between complex astrophysics and everyday understanding without oversimplifying the science. Documentaries have already begun demystifying the phenomenon. Take the BBC's recent Cosmic Frontier, which used stunning visualizations to map the cloud's path through our galactic neighborhood. By animating the heliosphere as a shimmering, dynamic shield, one that breathes and flexes like a living organism, they turned abstract concepts into something visceral. But visuals alone aren't enough. Podcasts like Interstellar Coffee Break distill the latest research into conversational episodes, featuring astronomers debating the cloud's potential impacts over casual interviews. The key is variety. A TikTok explainer might use humor to debunk myths, while a museum exhibit could let visitors touch interstellar gas through haptic feedback displays. Accessibility goes beyond language barriers. It's about meeting people where they are. In regions with limited internet access, community radio broadcasts could share updates in local dialects, while public libraries might host stargazing nights with telescopes tuned to highlight the cloud's chemical signatures. For younger audiences, games like Heliosphere Defender, where players reinforce a virtual shield against cosmic rays, make learning interactive. Even social media trends have a role. Imagine a viral challenge where users film creative interpretations of the heliosphere using household items, from water balloons to magnetic slime. The stakes are higher than mere curiosity. Misinformation spreads faster than light in the digital age, and cosmic phenomena are ripe for distortion. Conspiracy theorists could spin tales of alien invasions or government cover-ups, while well-meaning but inaccurate posts might exaggerate risks. Countering this demands proactive collaboration. Scientists partnering with platforms like YouTube or Douyin could embed verified explainers directly into search results about the cloud. Fact-checking initiatives, similar to those developed for climate change education, might train local ambassadors to debunk myths in culturally relevant ways, using analogies rooted in agricultural cycles for rural communities or tech metaphors for urban audiences. What makes this moment unique is the opportunity to redefine science communication itself. Traditional models often treat the public as passive recipients of knowledge, but the cloud's multi-century timeline invites ongoing dialogue. Citizen science projects could crowdsource data, like tracking subtle changes in night sky brightness that might signal the cloud's influence. Open-source tools could let classrooms worldwide run their own simulations, comparing predictions with real-time data from space probes. The goal isn't just awareness, but participation, transforming a global audience into active witnesses of a cosmic event that will shape humanity's future. The ultimate test lies in ensuring no one gets left behind. Indigenous astronomers, for instance, bring millennia of celestial observation traditions that could enrich Western models with forgotten insights about long-term cosmic patterns. Meanwhile, educators in developing nations need resources to integrate interstellar science into curricula without expensive equipment. Initiatives like UNESCO Starlight Kit program, which distributes low-cost spectroscopy tools, show how equity can be woven into outreach. After all, the cloud doesn't discriminate by borders or economies. It's a shared frontier, and understanding it should be too. By weaving science into culture, through art, storytelling, and collective problem-solving, we're not just preparing for a celestial event. We're building a blueprint for how humanity faces cosmic challenges together, with curiosity as our compass and collaboration as our engine. The interstellar cloud isn't just approaching our solar system, it's inviting us to rethink how knowledge travels, who gets to hold it, and what we're capable of when we all look up at the same sky. As we stand at the crossroads of this cosmic encounter, the interstellar cloud drifting toward us isn't just a scientific curiosity, it's a mirror reflecting humanity's resilience and ingenuity. For centuries, we've gazed at the stars as distant, unchanging points of light, but now we know better. The galaxy breathes, shifts, and evolves, and our solar system is no exception. This cloud, a wisp of ancient stardust, carries with it a profound lesson. The universe is not a static stage, but a dynamic participant in our story. Its arrival isn't an ending, it's an invitation to rethink our place in the cosmos and the legacy we'll leave for generations to come. What makes this moment so extraordinary is the duality it presents. On one hand, the cloud's pressure on our heliosphere could test the limits of our technology and adaptability. On the other, it offers a front-row seat to a process that shaped planetary systems across the Milky Way. Imagine the insights we'll gain as we watch, for the first time in recorded history, how a solar system responds to interstellar forces. Will our heliosphere bend, ripple, or rebound? The answers could redefine everything from astronaut safety to the search for life beyond Earth. This isn't just about survival, it's about unlocking secrets buried in the fabric of space itself. The true power of this encounter lies in how it unites us. Across continents and cultures, scientists, artists, engineers, and dreamers are turning their attention to the same patch of sky, each contributing a piece to the puzzle. A student in Mumbai running simulations, an engineer in Oslo testing radiation shields, a poet in Buenos Aires weaving cosmic metaphors, all are part of a collective effort to meet the unknown with curiosity rather than fear. History shows that humanity's greatest leaps often come when we're challenged by forces beyond our control. The interstellar cloud is that rare catalyst, pushing us to innovate not just for today, but for a future we'll never see. So as the cloud's slow approach unfolds across centuries, remember this: we are the first generation to witness such an event with eyes wide open, armed with the tools to understand and influence its outcome. The choices we make now, how we fund research, share knowledge, and inspire the next generation will echo far beyond our lifetimes. Whether we become cosmic architects, fortifying our solar system's defenses, or interstellar storytellers, preserving this chapter for those who follow, one thing is certain: the universe has handed us a question. How we answer it will define not just the future of our heliosphere, but the very soul of our species, the star.